Characteristics of Fraunhofer single slit diffraction. Point-wise, I can say a central bright maxima at O, followed by alternate secondary maxima and minima on either side. This is the central maxima, then secondary maxima, minima, then minima on either sides. The width of central maxima is twice of a secondary maxima. This is the width of central maxima is twice of the secondary maxima. The intensity of secondary maxima goes on decreasing with the increase in the order of maxima. As the order increases, the intensity of the secondary maxima decreases. Now, intensity of single slit diffraction. We can calculate the intensity I is equal to I naught sine square beta by beta square, where the term beta is equal to pi d sine theta by lambda. D is the slit width, lambda is the wavelength of light used. Theta is the angle of bending. You can come back to the slide. Here theta is the angle of, this is the theta, the angle of bending. So angle through which the light is bent. Now I naught is the maximum intensity at theta is equal to 0, as sine theta tending to 0, sine beta by beta, it becomes 1. We can show you in central maximum calculation. When theta is equal to 0, beta is equal to 0, limit beta tends to 0, sine beta by beta is equal to 1. Thus I is equal to I naught. Secondary maxima, the combining the solution, sine beta is equal to plus 1 and sine beta is equal to minus 1. We can write a simpler form. Beta is equal to sine beta plus 1 means sine 90 degree. That means n is equal to 0 means pi by 2, n is equal to 1 means 3 pi by 2, and so on. So sine beta is equal to minus 1. So combining this, you can write beta is equal to 2n plus minus 1 pi by 2. Now beta is equal to, this is the beta, pi d sine theta by lambda. So putting this one, you can find out d sine theta is equal to 2n plus minus 1 lambda by 2. So this is the condition of the secondary maxima. First order and other maxima will produce at, there is minima I am discussing later. This is 3 pi by 2, then 5 pi by 2, 7 pi by 2, and so on. At the left hand side also 3 pi by 2, 5 pi by 2, 5 pi by 2, and 7 pi by 2. The intensity of the first order secondary maxima I1 is equal to, putting this value, I naught sine square beta, beta means 3 pi by 2, then 3 pi by 2 whole square is equal to I naught by 22. Second order secondary maxima, putting 5 pi by 2, beta is equal to 5 pi by 2, I naught, I2 becomes I naught by 62. So it is evident that the intensity is decreasing from central maxima toward the first order second order maxima. It is decreasing in Fraunhofer single slit diffraction. Now what the minimas will form? Now sine beta is equal to 0. What the minimas will form? If beta is equal to sine beta 0, then I will be 0. I will be 0. So then sine n pi. But n is equal to 0. Already we have used it for central maxima. So n will start from 1. Plus minus 1, plus minus 2, plus minus 3, and so on. So beta becomes, so sine beta 0 minus sine n pi. So beta is equal to n pi. So beta means pi d sine theta by lambda is equal to n pi. Thus d sine theta is equal to n lambda. So this is the condition for the secondary minimum. So this is how the diffraction pattern is produced. This is the central maxima with maximum intensity. First order secondary maxima, its intensity is decreasing by I naught by 22. Then secondary maxima, second order secondary maxima, its intensity decreasing by I naught by 62, and so on. come to the next slide. Position of secondary maxima by graphical method. To do this, we will differentiate the expression of intensity I with respect to beta, and we will put di by d beta is equal to 0. So I, as we know, I is equal to I naught sine square beta by beta square. So after differentiating, we will get tan beta by beta. Tan beta is equal to beta. This equation gives the position of maxima. Here there are two equations, y is equal to tan beta, another one is equal to y is equal to beta. We will plot, this is the y is equal to tan beta and this one is y is equal to beta. So the intersecting points of y is equal to tan beta and y is equal to beta will give us the first order, second order maximum. We can see from the graph, the intersecting points are beta is equal to plus minus 1.435, plus minus 2.465 and so on. That means the root beta is equal to 0 corresponds to central maxima. This is the beta is equal to 0 correspond to central maxima. And other points, this is the point, it is not exactly 3 pi by 2, it is 1.43 pi. It will give us the first order secondary maximum. And next one will not exactly 5 pi by 2, it is 2.46 pi. It will give us the second order secondary maximum. So this is how we can find out the points or the secondary maximas will produce, and it can be find out graphically. Thank you.